The argument has been running for decades, and the scientists closest to it still cannot settle it. Not because they lack the instruments, not because they lack the data, but because the object at the center of the dispute sits 9,500 light-years from Earth. It is variable. It is shrouded in its own expelled material, and every measurement made of it rests on a chain of inference long enough that a small error at any link changes the answer at the end. In 2013, a team working with the Very Large Telescope Interferometer in Chile published a direct angular diameter measurement and derived a radius more than 1,700 times that of our Sun, large enough, if placed at the center of our solar system, to swallow every planet out to Jupiter and press towards Saturn. Other researchers looked at the same object with updated distance data and got a smaller number. Then, a different team revised the atmospheric model and got a different number still. The error bars on the leading estimates overlap. The record, officially, remains unclaimed. Nobody agrees on how big this star actually is. When the Gaia satellite released its revised parallax catalogue, the assumed distance shifted, and with it, every size calculation ever built on top of that distance. The star is called UY Scuti, and it may or may not be the largest known object of its kind. Tonight, we will trace the measurement, confront the physics, and follow the science to the edge of what stars are permitted to become. If this is the kind of journey you want to take, subscribe and leave a like. It genuinely helps. The question is not just how big this star is. The question is whether, across 9,500 light-years of gas and dust and uncertainty, we are even capable of knowing. Think about what it would mean to hold the record for something and not know it. To have your name at the top of a list that nobody can quite verify. To be the largest, or possibly the second largest, or possibly something else entirely, depending on which team you ask, which instrument they used, and what assumptions they fed into their models before the measurement even began. That is the situation with UY Scuti. It sits in the constellation of Scutum, roughly 9,500 light-years from where you are right now. It is a red hypergiant, a category of star so extreme that the word giant, applied to a star like our Sun, would be laughable in comparison. It is deep orange in color, unstable, pulsating, shedding its own mass into the space around it. And depending on which published estimate you consult, it is either the largest known star in the Milky Way or one of several candidates whose error bars overlap so substantially that no definitive ranking is possible. The number most often cited is a radius of approximately 1,708 times that of our Sun. Let that settle for a moment. Our Sun is roughly 1,400,000 kilometers across. A star 1,700 times larger would have a diameter approaching 2 billion kilometers. If you placed UY Scuti at the center of our solar system, in the position currently occupied by the Sun, its surface would extend past Mercury, past Venus, past Earth, past Mars, past the asteroid belt, past Jupiter. It would reach toward the orbit of Saturn and stop somewhere in that vicinity, depending on which phase of its pulsation cycle you happen to catch it in. You would not be able to see the star. You would be inside it. And yet that number, 1,708 solar radii, is contested. The people who produced it were careful, methodical scientists, working at the limits of what their instruments could resolve. The uncertainty attached to their measurement is not a footnote. It is large enough, when propagated through the calculation, to shift the star's ranking entirely. This video is about that number, how it was produced, what it rests on, why it remains disputed, and what the dispute itself reveals about the science of measuring things at the edge of what physics allows. There is a question that sounds simple and turns out to be one of the hardest problems in observational astronomy. How large is a star? Not our Sun. The Sun is close enough that we can measure its angular diameter directly and with great precision. It subtends roughly half a degree of sky as seen from Earth. And from that angle, and our known distance from it, its physical radius follows straightforwardly. The Sun is easy. The Sun is on our doorstep. Everything else is a different matter entirely. The stars you see on a clear night are not disks. they are points. Even through the most powerful conventional telescopes, they remain points. Their angular sizes are simply too small to resolve directly. A star like Betelgeuse, one of the largest and nearest red supergiants, subtends an angle of roughly 50 milliarcseconds as seen from Earth. That is 50,000ths of an arcsecond, an arcsecond being 1/3600th of a degree. To put that in terms you can feel, if you held a €1 coin at arm's length, Betelgeuse's apparent disk would fit inside that coin roughly 4 million times over. And Betelgeuse is one of the easiest stars to measure. It is among the nearest, among the largest, among the brightest. UY Scuti is far more distant and far dimmer in apparent terms. Its angular diameter is smaller still. The history of measuring stellar sizes directly begins in 1921 on a mountain above the Mojave Desert in California. The Hooker telescope at Mount Wilson Observatory was, at the time, the largest telescope in the world. Its mirror, 100 inches across, completed in 1917 and responsible for some of the most consequential observations in the history of astronomy. But the Hooker telescope alone could not resolve a stellar disk. It was not a limitation of the mirror's quality. It was a fundamental limit imposed by the wave nature of light. Albert Michelson understood this. Michelson was among the most meticulous experimental physicists of his era, the first American to win the Nobel Prize in Physics, awarded for his measurement of the speed of light. He knew that to resolve an angular size smaller than a single telescope's diffraction limit, you needed a longer baseline. You needed to separate your light collecting points by a distance greater than any single mirror could span. The technique he and his colleague Francis Pease applied was interferometry. Two small mirrors were mounted on a steel beam attached to the front of the Hooker telescope, separated by 20 feet. Light from a star entered both mirrors simultaneously and was directed to a common focus. Where the two beams overlapped, they interfered with each other, producing a pattern of alternating bright and dark fringes. The spacing of those fringes encoded information about the angular size of the source. When the source is a perfect point, the fringes have maximum contrast. As the source grows in angular size, the contrast of the fringes decreases. At a specific angular diameter, one that depends on the wavelength of light and the separation between the mirrors, the fringes disappear entirely. That disappearance is the measurement. Michelson and Pease pointed their interferometer at Betelgeuse in December of 1920. The fringes vanished. From the baseline at which they disappeared and the wavelength of the light, they derived an angular diameter of approximately 47 milliarcseconds, a number that has been refined many times since, but remains in the right territory a century later. It was the first direct measurement of a star's physical size. Think about what that means. A measurement of a disk so small it is invisible to every telescope on Earth, achieved by watching light waves cancel each other out. That technique, interferometry, is the foundation of everything that follows in this story. It has been refined, extended, moved into space, and rebuilt from the ground up with modern optics and digital detectors. But the principle Michelson established in 1921 is the same principle used to measure UY Scuti 92 years later. The geometry is identical. The physics is identical. The challenge, resolving an almost impossibly small angular size at an almost impossibly large distance, is identical. What changed was the scale of the baseline. And with a longer baseline comes both greater resolution and, as you will see, a new set of complications. The other thing Michelson's measurement established, and this matters enormously for everything that follows, is that measuring a stellar angular diameter is only half the problem. The Michelson-Pease result gave an angle. To convert that angle into a physical radius, an actual distance in kilometers or solar radii, you need to know how far away the star is. You need the distance. And measuring the distance to a star 9,500 light-years away is a problem of an entirely different order. The paper was published in 2013 in the journal Astronomy and Astrophysics. The lead author was Begoña Arroyo Torres, working with colleagues at the Universidad Complutense de Madrid and collaborating institutions. The title was precise and technical, as papers of this kind tend to be. It described the atmospheric structure and fundamental parameters of three red supergiants, AH Scorpii, UY Scuti, and KW Sagittarii. But it was the UY Scuti result that travelled. The instrument used was the AMBER spectrograph on the Very Large Telescope Interferometer, the facility operated by the European Southern Observatory on Cerro Paranal in the Atacama Desert of northern Chile. Paranal sits at an altitude of 2,635 meters in one of the driest and most stable patches of atmosphere on Earth, chosen precisely because atmospheric turbulence is the enemy of high-precision optical measurement. The site sees fewer than 10 nights of cloud per year. The seeing, the technical term for atmospheric steadiness, is among the best on the planet. The Very Large Telescope Interferometer works by combining the light from multiple individual telescopes, separated by distances of up to 200 meters, into a single coherent beam. That separation, the baseline, determines the angular resolution. A 200-meter baseline at near-infrared wavelengths gives you an angular resolution of roughly 1 milliarc-second. That is fine enough to resolve stellar disks for a handful of the largest and nearest red supergiants. UY Scuti sits right at the edge of what this instrument can do. The AMBER instrument operates in the near-infrared at wavelengths between 1 and 2.5 micrometers. This choice is not arbitrary. Red hypergiants are cool. UY Scuti has a surface temperature of roughly 3,200 Kelvin compared to the Sun's 5,778 Kelvin, and they emit most of their radiation in the infrared. Measuring at these wavelengths captures the star's emission most efficiently and avoids the wavelengths at which its circumstellar dust, the material it has been shedding for millions of years, is most opaque. What the team measured was the angular diameter of UY Scuti's photosphere, the visible surface, or as close to a surface as a diffuse gaseous object like a hypergiant can be said to have. The measurement gave an angular diameter of 5.48 plus or minus 0.1 arc milliseconds. From that angle and an assumed distance, they derived a linear radius. Here is where the first complication enters. The distance to UY Scuti used in the Arroyo Torres analysis was drawn from earlier catalogues, estimates based on the star's apparent brightness, its spectral type, and assumptions about its intrinsic luminosity. These indirect distance estimates carry their own uncertainties. The team used a distance of approximately 1.9 kiloparsecs, roughly 6,200 light-years in the units more familiar to most listeners, which already differs from some other estimates in the literature and differs significantly from what Gaia would later suggest. The derived radius came out at 1,708 solar radii, with an uncertainty of plus or minus 192 solar radii. That error bar spans nearly 400 solar radii from bottom to top. It is not a small uncertainty. It is large enough, if the true value sits near the lower end of the range, to place UY Scuti below other known red hypergiants that have been measured with different methods or at different epochs. There is a second complication that the paper itself is careful to acknowledge. The angular diameter measurement was made at a single point in time. UY Scuti is a semi-regular variable star. Its outer layers swell and contract on timescales of months to years, driven by pulsation mechanisms deep within the star. The radius at the moment of observation may not be representative of its mean radius. A measurement made 6 months earlier or 6 months later, during a different phase of the pulsation cycle, might give a number that differs by hundreds of solar radii. A third complication concerns the atmospheric model used to convert the raw angular diameter into a physical radius. The photosphere of a red hypergiant is not a sharp, well-defined surface. It is a thick, extended, dynamic atmosphere where the density falls off gradually with altitude rather than dropping abruptly at a clean boundary. Deciding where the stellar radius ends and the circumstellar environment begins is itself a modeling choice, and different choices produce different numbers. Émilie Lévesque had already demonstrated something relevant here in 2005. Working through the red supergiant population of the Milky Way, she and her collaborators found that the effective temperature scale that had been applied to these stars for decades was systematically wrong. The stars had been assumed to be cooler than they actually were. Correcting the temperature scale changed the derived luminosities, and changing the luminosities changed the inferred radii. The revision was not enormous for any single star, but it was consistent across the class, and it was in the direction of making the stars somewhat smaller than previously thought. The Arroyo-Torres paper is careful science. It is not inflated or sloppy. The authors present their uncertainties clearly and acknowledge the limitations of a single epoch measurement of a variable star at the edge of their instrument's capability. The number that left the paper and entered the popular science literature, 1,708 solar radii, largest known star, was a real result with real support. But real support is not the same as certainty, and the chain of inference between the raw measurement and that headline number has links that, when pulled, give a little. That is the nature of the problem. Not that the science was done carelessly, but that the object being measured is 9,500 light-years away, variable, surrounded by its own expelled atmosphere, and located in one of the most dust-obscured regions of the Milky Way. Under those conditions, a measurement this difficult being this close to right is itself a remarkable achievement. The question is whether close to right is close enough to settle the record. And as the years passed and new data arrived, the answer began to look increasingly like no. It is worth dwelling on why distance is so consequential here, not just as a caveat, not as a footnote to the main story, but as the central structural problem of stellar size measurement at this scale. When you derive the physical radius of a distant star, you are not measuring it directly. You are measuring an angle, the angular diameter, and then multiplying that angle by a distance to get a length. The relationship is simple geometry, but simple geometry becomes unforgiving when one of your inputs carries uncertainty. If the distance is wrong by 15%, the radius is wrong by 15%. There is no buffer, no correction factor, no way to absorb the error. It flows through the calculation with perfect fidelity. For UY Scuti, sitting nearly 10,000 light-years away in one of the most obscured regions of the inner Milky Way, distance has always been the hardest number to pin down. Before Gaia, distances to stars at this range were estimated through a combination of methods, none of them direct. You could measure a star's apparent brightness and its spectral type, infer its intrinsic luminosity from those properties, and then use the relationship between apparent and intrinsic brightness to back-calculate a distance. This approach, known as spectrophotometric distance estimation, works tolerably well when you know the intrinsic luminosity precisely. For red hypergiants, you do not. Their luminosities vary as they pulsate. Their spectral types shift as their surface temperatures change. And the dust between us and the star absorbs and scatters light in ways that are difficult to account for without independent knowledge of the dust column, knowledge that is itself uncertain. The result was a range of pre-Gaia distance estimates for UY Scuti that spanned a meaningful interval. Different groups, using slightly different methods and slightly different assumptions, produced numbers that disagreed by enough to matter. The Arroyo-Torres team selected a specific value from this range. Had they selected a different value from within the same plausible interval, their derived radius would have been different. The measurement was real. The distance it rested on was an informed estimate. Gaia changed this picture substantially. The mission, whose data releases were coordinated by Anthony Brown at Leiden Observatory and overseen at the mission level by project scientist Timo Prusti at the European Space Agency, produced parallax measurements for over 1 billion stars. The satellite operates from a position far from Earth's atmosphere, scanning the sky continuously, returning to each star dozens of times over the course of its operational life. The result is a statistical picture of each star's position built from repeated observations, and from that picture, a parallax. The principle is the same geometry that underlies every stellar distance measurement since the 19th century. As Earth orbits the Sun over the course of a year, nearby stars appear to shift slightly against the background of more distant objects. The size of that shift, the parallax angle, reveals the distance directly, without assumptions about the star's intrinsic brightness or spectral properties. Larger shift, closer star. Smaller shift, further away. No inference about luminosity required. For nearby stars, Gaia's parallaxes are extraordinarily precise. For stars at several thousand light-years, the precision remains impressive, but the fractional uncertainty grows. The parallax angle of UY Scuti is close to the limits of what Gaia can resolve reliably. The angle is tiny, the star is faint at the wavelengths Gaia observes, and the dense stellar field of the inner Milky Way introduces additional complications in the data processing. The result Gaia returned placed UY Scuti at a distance that, when fed into the Arroyo-Torres angular diameter, gave a smaller radius than the original paper had reported. The difference was not catastrophic. The star does not suddenly become unremarkable, but it was enough to erode confidence in the headline figure and to push UY Scuti's size estimate into territory where it overlaps with those of its closest rivals. Here is where the problem compounds. A star's radius can be calculated two ways. The first is the direct geometric route, angular diameter multiplied by distance. The second uses the Stefan-Boltzmann law, which describes the relationship between a radiating object's temperature, surface area, and total power output. If you know how intrinsically luminous a star is and how hot its surface is, you can calculate how large it must be to produce exactly that combination of temperature and brightness. The two methods should agree. In practice, they each carry their own uncertainties and sometimes diverge. The Gaia distance revision fed into both routes simultaneously. A closer distance means a lower intrinsic luminosity. The star does not need to be as powerful to appear as bright as it does from Earth. A lower luminosity, combined with the same surface temperature, implies a smaller radius via the Stefan-Boltzmann route. So the Gaia result did not simply modify one number in one calculation. It propagated through every pathway that leads to a size estimate, nudging each one toward a smaller answer. What the distance problem reveals is that the size record is not a number waiting to be confirmed. It is a problem waiting to be solved. Solving it properly will require a convergence of measurements from different instruments at different wavelengths at different epochs, all pointing to the same answer within uncertainties small enough to be decisive. That convergence does not yet exist. There is something almost paradoxical about UY Scuti's variability. A star so large that changes in its radius, which would completely dwarf the Sun, happen quietly, over months, without dramatic visible display. It dims a little, it brightens a little. To an observer with a modest telescope, it looks like nothing more than a faint red star doing what variable stars do. Underneath that apparent calm, something genuinely restless is happening. UY Scuti is classified as a semi-regular variable. This places it in a category of stars whose brightness fluctuates in a roughly periodic way, but without the precise clockwork regularity of other variable types. A Cepheid variable pulses with a period so stable and so predictable that it functions as a cosmic distance standard. The same star, measured at different times, will complete its cycle with extraordinary consistency. Astronomers can use it as a ruler. UY Scuti does nothing of the kind. Its variations follow a dominant period, but that period is overlaid with secondary cycles and irregular departures that make any single observation a snapshot of a complex, multi-layered dynamical system rather than a well-defined point on a predictable curve. Laszlo Kiss, working with colleagues at the Konkoly Observatory in Budapest, analyzed the long-term photometric record of UY Scuti as part of a broader study of hypergiant variability. The work drew on historical brightness measurements spanning decades, from professional survey programs and from the accumulated records of amateur observers who had been monitoring this and similar stars with steady patience over years. From this archive, Kiss and his team extracted the underlying periodicities through period analysis, identifying the dominant oscillation timescales buried within the noise of individual observations. The dominant period came out at roughly 740 days, just over 2 years. But the star also shows evidence of a shorter secondary period, and the amplitude of its fluctuations is not constant from cycle to cycle. Sometimes the dimming is more pronounced. Sometimes the variation is subdued. The outer envelope is not following a single clean oscillation driven by a single mechanism. It is the product of multiple interacting physical processes: pulsation, convection, episodic mass loss, each operating on its own timescale and contributing to the overall behavior in proportions that shift over time. Now consider what that means for the 2013 interferometric measurement. The Arroyo Torres team observed UY Scuti at a specific point in time, a single epoch. They derived a single radius from it. That radius is real. It reflects what the star's photosphere was doing on the nights the data were taken. But it is not the star's mean radius. It is not the maximum the star achieves during a pulsation cycle. It is not the minimum. It is one frame of a film that runs across a roughly 740-day cycle with additional irregularity layered on top. If the observations happen to catch UY Scuti near the peak of its expansion, the point at which the outer envelope has swelled furthest, the derived radius would sit toward the high end of the star's natural range. If the star was near minimum contraction, the number would be smaller. Without detailed prior photometric monitoring at the relevant epochs, placing the observation within the pulsation cycle is genuinely difficult. Even for Betelgeuse, our nearest red supergiant, monitored continuously by telescopes around the world for decades, pinning down a single definitive radius is complicated by variability. Different observational campaigns return numbers that scatter around a central value, and that scatter is not experimental error. It is the star actually being different sizes at different times. For UY Scuti, 9,500 light-years away and far harder to observe, the monitoring baseline is far thinner. Characterizing its variability range with confidence requires sustained observation over multiple complete pulsation cycles. That work is ongoing, and it is not yet done. What KISS's analysis establishes is that UY Scuti's radius is not a number, it is a range with a center, poorly constrained, and a width that extends over hundreds of solar radii from minimum to maximum. The uncertainty of plus or minus 192 solar radii, quoted in the Arroyo Torres paper, captures the measurement precision of the interferometric observation. It does not fully capture the additional uncertainty introduced by catching a pulsating star at an unknown phase. The true spread of plausible values is wider than the stated uncertainty suggests. Not because the Arroyo Torres team was careless, they were not, but because quantifying pulsational phase uncertainty requires a kind of long baseline photometric campaign that simply did not exist for UY Scuti at the time the interferometric measurement was made. Here is the difficulty stated plainly. The most precise direct measurement of UY Scuti's size is simultaneously a measurement of a moving target taken at an unknown moment in its cycle, resting on a distance estimate that has since been revised, derived using an atmospheric model that introduces its own layer of assumption. Each of those factors individually would be manageable. Together, they build a case for treating the published number with genuine respect for what it achieved and genuine caution about what it claims. The record stands, but it stands on ground that shifts. And UY Scuti is not even the only candidate. That is the part of this story that tends to get lost when the subject is reduced to a single headline. There is a list. It is not a short list. And the names on it are not also RANs separated from the title by a comfortable margin. They are stars whose size measurements, within their stated uncertainties, either match UY Scuti's or exceed it, depending on which study you consult, which instrument produced the data, and which set of assumptions went into the calculation. The record is not one star standing clearly above the rest. It is a cluster of candidates pressed together at the top of a ranking that nobody has the precision to resolve. Stephenson 218 sits in the same region of the sky as UY Scuti, embedded in the dense stellar fields of the Scutum star cloud. It was identified in a catalogue compiled by Charles Bruce Stephenson at the Warner and Swazi Observatory in Ohio, and for a long time it attracted relatively little attention compared to the more widely discussed red hypergiants. Then, as distance estimates were revised and the star's properties were examined more carefully, it emerged as a serious contender, some studies placing its radius above 2,000 solar radii, which would make it larger than UY Scuti by any current estimate. But those numbers carry the same problems. Stephenson 218 is even more deeply embedded in a region of intense dust obscuration than UY Scuti, making its apparent brightness difficult to interpret, its distance harder to pin down, and its angular diameter impossible to measure directly with current instruments at its distance. The radius estimates for Stephenson 218 are derived almost entirely from luminosity and temperature, not from interferometric angular diameter measurement. That makes them less direct, and in some respects less reliable, than the Arroyo-Torres result for UY Scuti, but they cannot be dismissed. Then there is VY Canis Majoris. For decades, before UY Scuti rose to prominence in the popular science literature, VY Canis Majoris was the name most commonly attached to the question of which star is largest. It is closer than UY Scuti, roughly 4,000 light-years away, well within the range where direct interferometric measurement is more tractable, and it has been observed extensively across multiple wavelengths and at multiple epochs. Current estimates place its radius at roughly 1,400 solar radii, somewhat below the Arroyo-Torres figure for UY Scuti. But those estimates have themselves been revised repeatedly. Earlier studies gave numbers substantially larger. The revisions came as distance estimates improved, and as the understanding of how the star's extended circumstellar envelope complicates the definition of its photosphere deepened. VY Canis Majoris is one of the most extreme mass-losing stars known. It is surrounded by an extraordinarily complex nebula of gas and dust, a record of its past eruptions, shaped into arcs and knots and filaments by the interaction between successive ejection events and the surrounding medium. Keiichi Onaka and colleagues at the Max Planck Institute for Radio Astronomy have produced some of the most detailed resolved observations of this star and its environment, revealing structure in the circumstellar material that speaks to a history of violent, episodic mass loss events spread over thousands of years. What those observations also reveal is that drawing a clean boundary between the star itself and the material it has expelled is not straightforward. The photosphere fades into an extended, dusty atmosphere that extends far beyond any reasonable definition of a stellar surface. That boundary problem, deciding where the star ends and the envelope begins, afflicts every red hypergiant to some degree. For VY Canis Majoris, it is particularly acute, and wherever the boundary is drawn, the number changes. WOHG 64 presents a more extreme version of the same problem. This star sits not in the Milky Way, but in the Large Magellanic Cloud, a satellite galaxy roughly 160,000 light-years from Earth. At that distance, direct angular diameter measurement is completely beyond the capability of current interferometers. Everything we know about WOHG 64's size comes from indirect inference: its luminosity, its temperature, its spectral type. Those inferences suggest a star comparable in size to UY Scuti, perhaps larger. But they also suggest that WOHG 64 is surrounded by one of the most massive circumstellar dust tori ever observed around a single star, a disk of ejected material so thick that it obscures the optical photosphere almost entirely. The radius you would infer from the star's luminosity and temperature is the radius of the stellar interior. The radius of the visible object, if you could observe it at optical wavelengths, would be different, larger, and shaped as much by the surrounding dust as by the star itself. WOHG 64 illustrates a boundary that runs through this entire discussion. The question of how large a star is turns out to be inseparable from the question of where a star ends. For objects that are actively dismantling themselves, shedding mass at rates that create extended, optically thick envelopes over millions of years, that question has no clean answer. And then there is a different kind of record entirely. R136A1 sits at the heart of the R136 cluster in the Tarantula Nebula, a star-forming region in the Large Magellanic Cloud so productive that it would outshine everything else in the night sky if it were as close to us as the Orion Nebula. R136A1 is not the largest star by radius. It is the most massive. Paul Crowther at the University of Sheffield led the analysis that placed its mass at somewhere between 150 and 300 solar masses, a range that itself reflects the difficulty of measuring the properties of an object this extreme. At those masses, the star blazes with a luminosity millions of times that of the Sun. It is hot, compact, and intensely blue. Its radius is a few tens of solar radii, enormous by ordinary stellar standards, but negligible compared to UY Scuti. This distinction matters enormously, and it is one that popular accounts of the largest star question consistently collapse. Mass and physical size are not the same thing. A star's radius depends on both its mass and its temperature. A very massive star that burns hot, a blue supergiant or a Wolf-Rayet star, can be physically smaller than a much less massive star that has expanded and cooled into the red hypergiant phase. UY Scuti is almost certainly less massive than R136A1 by a considerable margin. Its current mass is estimated at somewhere between 7 and 32 solar masses, the wide range reflecting how much of its original mass it has shed over its lifetime. But it is physically far larger because it is cool. Its surface temperature of roughly 3,200 Kelvin causes the same luminosity to be spread over a vastly greater surface area. The size record and the mass record are held by different stars. They will probably always be held by different stars. Confusing the two produces a ranking that means nothing scientifically. What the list of rivals demonstrates, taken together, is that the question of which star is largest is genuinely open, not because the science is poor, but because the objects are extreme, distant, variable, and self-obscuring. The rankings will shift as instruments improve. For now, UY Scuti holds a provisional title in a competition whose final result has not been declared. To understand why this region of the Milky Way produces objects of such extraordinary scale, you need to know something about where UY Scuti actually lives. Point a telescope at the constellation of Scutum on a clear, dark night, and you are looking toward one of the most densely packed stellar environments in the galaxy. The stars here are not simply numerous, they are, in many cases, extreme. The products of a stellar nursery that has been generating massive objects for millions of years in conditions that favor size, violence, and brief lives. The Scutum Centaurus arm is one of the Milky Way's two primary spiral arms, sweeping through the inner galaxy in a great curve that passes through this region of sky at a distance of roughly 8 to 10,000 light-years from Earth. It is a region of elevated molecular gas density, the raw material from which stars form, and of ongoing star formation activity. Molecular clouds here are among the most massive in the galaxy, capable of collapsing under their own gravity to produce not single stars, but entire clusters of stars simultaneously, including stars far more massive than the Sun could ever be. Embedded within this arm, within the region known as the Scutum star cloud, are two star clusters that tell you everything you need to know about how unusual this environment is. The first is designated RSGC1, Red Supergiant Cluster 1. The second is RSGC2. Both are young clusters by stellar standards, only a few million years old. Both are among the most massive star clusters in the Milky Way, and both contain concentrations of red supergiants so extraordinary that finding them was itself a discovery that forced astronomers to revise their assumptions about what stellar populations in this part of the galaxy could look like. Ben Davies, working with collaborators while at the University of Leeds, led surveys of these clusters that characterized their populations in detail. What those surveys found was a density of luminous red supergiants with no clear parallel in other nearby clusters. RSG C1 alone contains somewhere around a dozen confirmed red supergiants within a region of sky only a few arc-minutes across. RSG C2 contains more. These are not ordinary stars clustered by chance. They are the evolved descendants of a single massive burst of star formation, a population of high-mass stars, born together, now aging together, each tracking the same evolutionary path toward the red supergiant and hypergiant phases at roughly the same point in their lives. UY Scuti is not formally a member of either cluster. Its distance and position suggest it is part of the broader Scutum star cloud population, rather than belonging to one of the compact clusters specifically, but it inhabits the same galactic environment, formed from the same reservoir of dense molecular gas, and represents the same kind of extreme stellar evolution that the clusters have revealed is a routine feature of this region. The dense stellar environment of the Scutum star cloud has another consequence. Massive stars in crowded regions have a significantly higher probability of interacting with companion stars than isolated stars do. Binary and multiple star systems are common across the galaxy, but in high-density regions they are particularly prevalent, and many massive stars that appear isolated may have formed as binaries and subsequently lost their companions through gravitational interactions or through the death of one member of the pair. Binary interaction changes everything about a star's evolution. A massive star with a close companion can transfer mass to or receive mass from that companion at various points in its life, altering its total mass, its rotation rate, its chemical composition, and ultimately the path it takes toward death. Stars that would otherwise evolve along a standard single-star track can be sent onto radically different trajectories by a companion's influence. The result is a population of evolved massive stars in regions like the Scutum star cloud that is far more diverse and far more extreme than models built on isolated single-star evolution would predict. UY Scuti's past may include interactions we cannot now reconstruct. Its current properties, the mass we estimate, the radius we struggle to pin down, the rate at which it is shedding material, reflect not just its birth mass, but its entire history. In a region that generates objects like this routinely, that history is almost certainly more complex than any simple account of it would suggest. So how does a star become something like UY Scuti in the first place? The question sounds simple, but the answer requires following a chain of events that begins in a collapsing cloud of molecular gas millions of years before the star we see today came into existence. Understanding that chain, what conditions are needed at the start, what the star must survive along the way, and what it looks like when it finally arrives at the red hypergiant phase, turns out to be essential to understanding why objects like UY Scuti are so rare, why they are so extreme, and why their lives are so dramatically brief by cosmic standards. Start with the raw numbers. Stars form across an enormous range of masses, from objects barely large enough to sustain nuclear fusion up to monsters of 100 solar masses or more. But that range is not evenly distributed. The vast majority of stars that form are small, less than a single solar mass, often far less. Stars like the Sun, in the middle of the mass spectrum, are already comparatively uncommon. Stars of 10 solar masses are rarer still. Stars of 30, 40, 50 solar masses represent a tiny fraction of all the stars that have ever formed in the history of the Milky Way. And stars of the mass needed to eventually produce a red hypergiant, somewhere in the range of 20 to 40 solar masses at birth, though the upper end of that range is uncertain, are so scarce that the galaxy contains perhaps a few 100,000 of them at any given moment, spread across a disk of stars numbering in the hundreds of billions. Rarity is not the only distinguishing feature. These stars also burn fast. The relationship between a star's mass and its luminosity is steep. A star 10 times the mass of the Sun radiates roughly 10,000 times more energy. That energy comes from nuclear fusion in the core and the fuel supply, though vast in absolute terms, is consumed at a rate that scales with the luminosity rather than the mass. The result is that massive stars exhaust their core hydrogen in millions of years rather than billions. A star of 30 solar masses might live for only 5 or 6 million years in total, from birth to death. The Sun will live for roughly 10 billion. UY Scuti is already old by its own standards, and it has barely registered in the age of the galaxy. While the core hydrogen lasts, the star sits on what astronomers call the main sequence, the stable, well-defined band on the Hertzsprung-Russell diagram, where stars spend the bulk of their lives, fusing hydrogen to helium at a rate calibrated to balance the outward push of radiation pressure against the inward pull of gravity. A star of the mass range that eventually produces a red hypergiant occupies the hot, bright, blue end of that diagram during this phase. It is a blue or blue-white supergiant, luminous, compact by stellar standards, with a surface temperature that might reach 20,000 to 40,000 Kelvin. Then the hydrogen in the core runs out. This is the moment that everything changes. Without the energy released by hydrogen fusion to maintain pressure, the core can no longer support itself against gravity. It begins to contract. As it contracts, it heats, eventually reaching the temperatures needed to fuse helium into carbon and oxygen, the next rung on the nuclear ladder. But the response of the outer layers of the star to core contraction is counterintuitive. Rather than shrinking along with the core, the envelope expands. It expands dramatically, cooling as it does so, carrying the star's surface temperature down from tens of thousands of Kelvin toward 4, 5, 6,000 Kelvin, and eventually lower still. On the Hertzsprung-Russell diagram, this evolution appears as a rightward and upward march, the star growing in luminosity and cooling in surface temperature simultaneously, tracking a path that carries it from the blue supergiant region toward the red. This is the journey to the red supergiant, and eventually the red hypergiant phase. It is not a slow drift. On stellar timescales, it is relatively rapid, a matter of tens of thousands of years, quick enough that stars caught in this transition are rare simply because the transition does not last long. Not every massive star completes this journey cleanly. Norbert Langer, whose work at the University of Bonn has shaped much of the modern understanding of how massive stars evolve toward their deaths, has mapped the ways in which mass loss, rotation, and the influence of companion stars can divert a star from the standard evolutionary track. A star that loses mass rapidly enough during the blue supergiant phase may never reach the red hypergiant region at all. It sheds its outer envelope before it can expand, leaving a stripped, compact core that evolves toward death on a completely different trajectory. A star in a close binary system can transfer mass to or receive mass from its companion, altering its effective mass and the pressure balance in its interior, again changing the path it follows across the diagram. Philip Massey's comparative studies of red supergiant populations in the Milky Way and the Magellanic Clouds have shown that the properties of these stars, their temperatures, their luminosities, the range of masses they cover, depend sensitively on the environment in which they formed and the evolutionary models used to interpret them. The simple picture of a massive star expanding rightward across the diagram conceals enormous complexity. One aspect of that complexity deserves particular attention. The path to the red hypergiant phase is not necessarily one way. Some hypergiants are thought to evolve not steadily toward their deaths in the red part of the diagram, but back and forth across it, expanding and cooling into the red hypergiant phase, losing mass rapidly there, then contracting and heating back toward higher temperatures as the outer envelope thins before perhaps expanding again. Each crossing of the instability region at intermediate temperatures costs the star more of its remaining mass. Each passage changes the conditions in the interior. The star is not following a smooth evolutionary track. It is oscillating across the diagram, and its eventual fate depends on how much mass survives each crossing. UY Scuti's position in this story is uncertain. Whether it is making its first excursion into the red hypergiant phase, or has already crossed the diagram multiple times, is not something current observations can definitively answer. What is clear is that it has arrived somewhere close to the extreme end of stellar evolution, a place where stability is contingent, change is constant, and the boundary between the star and the space around it is actively in motion. In 1979, Roberta Humphreys at the University of Minnesota and Chris Davidson, her collaborator, published a survey of the most luminous stars in the Milky Way and the Magellanic Clouds. Their goal was to map where the most extreme stars sit on the Hertzsprung-Russell diagram and see what that distribution reveals about stellar evolution at the top of the mass range. What they found was a boundary. Above a certain luminosity threshold, corresponding roughly to 1,000,000 times the luminosity of the Sun, the upper right corner of the Hertzsprung-Russell diagram was essentially empty. Stars of very high luminosity existed across the diagram at blue and intermediate temperatures. But at high luminosities and cool temperatures simultaneously, the region where the most extreme red hypergiants would sit, there was almost nothing. A sparse scattering of rare objects, but no dense population. No stable sequence of cool, extremely luminous stars to mirror the well-populated main sequence at the hot end. This was not a gap caused by incomplete observations. The brightest stars in the sky are not easy to miss. The gap was real, and it required an explanation. Humphreys and Davidson argued that the boundary they had identified was physically meaningful, that stars could not persist in the upper right region of the diagram on any significant timescale. They proposed that above a critical luminosity, a star's outer layers become so loosely bound that radiation pressure from the interior begins to dominate over gravity's inward pull. The star responds by shedding mass, not in the steady, controlled way of a solar wind, but catastrophically, losing material in quantities large enough to change its luminosity and force it back toward the stable part of the diagram. The boundary, which has since carried their names, is a line that stars approaching from the blue side are pushed back from, and a line that red hypergiants pressing against it from the cool side are shedding mass to retreat from. To understand why radiation pressure becomes so destabilizing at high luminosities, consider a concept introduced by Arthur Eddington in the early 20th century. Eddington recognized that the outward pressure of radiation, light pushing on gas, must be balanced by gravity in any stable star. For a given stellar mass, there is a maximum luminosity at which that balance can be maintained. Exceed that luminosity, and radiation pressure overwhelms gravity. The outer layers cannot be held in place. They are driven off. This limiting luminosity depends on the star's mass and the opacity of its material to radiation. For very massive stars, it is enormous in absolute terms, but so is the star's actual luminosity. The two values sit uncomfortably close to each other. The margin between the luminosity the star actually produces and the luminosity that would blow it apart is narrow. In some extreme objects, that margin effectively vanishes. Red hypergiants, like UY Scuti, approach this limit from an unusual direction. They are not the most luminous stars known. Objects like Eta Carinae and the massive stars of the R136 cluster in the Tarantula Nebula outshine them enormously. But red hypergiants combine significant luminosity with very cool surface temperatures, and cool atmospheres are far more opaque to radiation than hot ones. Higher opacity means radiation pressure is more effective at driving mass loss per unit of luminosity. A red hypergiant can find itself at the Humphreys-Davidson limit, even at luminosities that would be perfectly sustainable for a hotter star of the same mass. The pulsations you see in UY Scuti, the swelling and contracting, the brightness changes over periods of hundreds of days, are a direct symptom of this precarious position. When a star's outer layers are barely gravitationally bound, small perturbations in the balance between gravity and radiation pressure send ripples through the envelope. Those ripples become the pulsations. The pulsations, in turn, drive mass loss, repeatedly lifting material away from the photosphere and into the region where radiation can carry it off entirely. The Humphreys-Davidson limit is not a wall. It is a boundary that stars cannot linger near. The stars we observe close to it are those in transit, crossing it rapidly, losing mass rapidly, and moving away from it in one direction or another. UY Scuti is one of those transiting objects. Its instability, its variability, its active mass loss, none of these are incidental features of its character. They are signatures of a star operating at the edge of what stellar physics permits. That edge is precisely what makes it so difficult to measure. An object that will not hold still, that is shedding its own outer atmosphere into the space around it, that is embedded in its own expelled material, is not easy to pin a radius on. But the instability itself tells you something true and important. UY Scuti is not simply very large. It is large because it is extreme. And it is extreme because it is standing at a boundary that the laws of physics have drawn in a place where very few stars are permitted to stand for very long. What that boundary demands, more than anything else, is material. And UY Scuti is paying. The sun loses mass. Every star does. The solar wind carries a steady stream of charged particles outward at roughly 400 kilometers per second. And over the course of a year, the sun sheds something in the region of 1/10 trillionth of its total mass through this process. Spread across a lifetime of 10 billion years, the total loss is significant but manageable. Perhaps a small fraction of the sun's original mass stripped away before it enters its own final stages billions of years from now. UY Scuti operates in a different regime entirely. The mass loss rate of red hypergiants is not measured in 10 trillionths per year. It is measured in units of solar masses per year, whole solar masses, or significant fractions of one, stripped from the star and expelled into the surrounding space over the course of 12 months. Estimates for UY Scuti's current mass loss rate vary across the literature, partly because mass loss rates are themselves difficult to measure precisely, and partly because they change over time as the star evolves. But even conservative figures suggest that UY Scuti is losing material at a rate orders of magnitude beyond anything a solar-type star experiences. In the time it takes you to read this sentence, the star has shed a quantity of gas and dust that dwarfs the combined mass of every planet in our solar system. Understanding why requires going inside the star's atmosphere. Eric Josselin and Bertrand Plez, working at the Université de Montpellier, produced one of the most detailed analyses of the atmospheric dynamics driving mass loss in red supergiants. Their work identified a combination of mechanisms acting together, each amplifying the effect of the others. The story begins with convection. Convection is the process by which hot material rises, cools, and sinks again in a continuous circulatory motion. The same process that drives weather patterns on Earth and that transports energy through the outer layers of the sun. In the sun, the convective zone is a shell occupying roughly the outer 30% of the solar radius. The convective cells, the individual rising columns of hot gas, are enormous by terrestrial standards, tens of thousands of kilometers across. But by the standards of what happens in a red hypergiant, they are modest. In a star like UY Scuti, the convective envelope extends deep into the star, and the individual convective cells are on a scale that defies ordinary intuition. Models suggest that a single convective cell in a red hypergiant could be larger than the entire sun, not the convective zone, a single cell within it. These enormous upwellings of hot gas carry not just energy, but momentum, creating turbulent pressure fluctuations that extend all the way to the photosphere and beyond. The atmosphere above the photosphere is not a calm, ordered place. It is churned by the passage of these titanic convective structures rising from beneath. The churning atmosphere creates the conditions for dust formation. In the cooler outer regions of UY Scuti's extended atmosphere, where temperatures drop low enough for certain molecular species to condense, tiny grains of silicate and carbonaceous material form. These dust grains are efficient absorbers and scatterers of radiation. When radiation from the star's interior pushes outward through the dusty outer atmosphere, the momentum transferred to the dust grains is transmitted to the surrounding gas, and the resulting outward force, acting across an enormous surface area at low gravity, is sufficient to accelerate material to escape velocity. This is the mechanism Jocelyn and Plez's work illuminated. Convection drives turbulence. Turbulence lifts material to the altitudes where dust forms. Radiation pressure on dust drives that material outward, and the star bleeds. The three components, convection, dust formation, and radiation pressure, work in concert, and each feeds the others. More convection means more turbulence. More turbulence means more efficient dust formation. More dust means more radiation pressure. More radiation pressure means more mass loss. More mass loss changes the structure of the outer envelope, which changes the convective dynamics, which changes everything again. Nathan Smith, surveying the full landscape of mass loss across massive star evolution from the University of Arizona, has placed this steady wind process within a broader framework. The continuous stellar wind of a red hypergiant is one end of a spectrum. At the other end are the violent episodic ejection events, the sudden expulsion of large masses of material in events that can dwarf the continuous wind over any comparable time period. Somewhere between these two extremes lie the surface mass ejection events, more intense than the wind, less total than a full eruptive outburst, that have been observed in detail around stars like Betelgeuse and VY Canis Majoris. The material expelled by UY Scuti does not simply disperse, it accumulates. Over millions of years of mass loss at elevated rates, a circumstellar envelope builds up around the star, a shell of gas and dust at progressively larger radii, the accumulated record of everything the star has shed since it entered this phase. This envelope has been detected around UY Scuti at infrared wavelengths. Its presence is not surprising. Every red hypergiant we have studied in detail has one. But its extent and density give indirect information about how long UY Scuti has been losing mass at its current rate, and what the total integrated mass loss has been over that period. That envelope also complicates the measurement problem discussed earlier. The photosphere, the visible surface of the star, the thing the interferometer measured, sits at the inner boundary of this extended dusty atmosphere. But the atmosphere does not have a clean inner edge. It grades continuously from the denser photospheric layers into the more tenuous circumstellar material at larger radii. Deciding exactly where one ends and the other begins is a modeling choice, and the choice affects the derived radius. In VY Canis Majoris, where the circumstellar environment has been imaged in detail at multiple wavelengths and epochs, the complexity of the ejected material reveals a history of individual mass loss events at different times, in different directions, at different rates. Arcs and knots and elongated filaments stretch outward from the star in a pattern recording the episodic, directionally variable nature of the mass loss over thousands of years. UY Scuti is almost certainly surrounded by comparable complexity. We simply cannot see it. The mass UY Scuti is losing now will not vanish. It will become part of the interstellar medium, the diffuse gas and dust between the stars. When UY Scuti eventually dies, the supernova or collapse event will slam into this pre-ejected material, interacting with it in ways that shape the light curve and the observable properties of whatever explosion occurs. The mass loss history being written now is the prologue to the death that is coming. Everything described so far, the pulsation, the mass loss, the instability, the position near the Humphreys-Davidson limit, applies to UY Scuti as a red hypergiant, as a cool, extended star in the lower right of the Hertzsprung-Russell diagram. But if UY Scuti continues to evolve, if it loses enough mass and contracts and heats, there is a region of the diagram it will eventually need to pass through. And that region is one of the most extraordinary features of stellar astrophysics that barely anyone outside the field knows exists. It is called the yellow hypergiant void. Cornelis de Jager at Utrecht Observatory produced the defining review of yellow hypergiants in 1998, a comprehensive survey of the small peculiar population of stars found at temperatures between roughly 5,000 and 8,000 Kelvin, and an explanation of why that temperature range is so uniquely hostile to stellar stability. His work established a framework for understanding not just what yellow hypergiants are, but why they cannot stay that way for long. The void refers to the striking absence of stable, long-lived hypergiants in a specific temperature band on the Hertzsprung-Russell diagram. Look at any well-populated version of that diagram, spanning the full range of stellar masses and temperatures, and you will see stars everywhere except in one region. In the zone corresponding to spectral types F and G, surface temperatures between roughly 5,000 and 8,000 Kelvin, hyperluminous stars simply do not persist. Individual objects are found there, briefly, but they do not stay. They are caught in transit, and transit through this region is violent. The physical explanation involves the behavior of hydrogen in the stellar atmosphere at these temperatures. In hotter stars, hydrogen is fully ionized, stripped of its electron, unable to absorb radiation in the ways that neutral hydrogen can. In cooler stars, hydrogen is neutral and its opacity, while present, is relatively predictable and well-behaved. In the intermediate temperature range of the void, hydrogen is in transition, partially ionized, with the ionization state changing sensitively as temperature varies. This produces a zone of dramatically variable opacity in the stellar atmosphere. Here is why that matters. A hypergiant's outer envelope is already only weakly held by gravity, already close to the threshold where radiation pressure begins to win. When such a star cools to the temperature range of the void, the partial ionization of hydrogen changes the opacity in a way that disrupts the balance between energy transport and pressure support in the envelope. The envelope becomes dynamically unstable. Instead of gently pulsating as red hypergiants do, the star undergoes rapid, violent structural changes. Mass loss rates spike dramatically. The envelope contracts and heats in response, pushing the star back out of the void toward higher temperatures. Or it collapses inward, and the star moves in the other direction. The void is not simply an empty region on a diagram. It is an active barrier. Stars are expelled from it by the violence of the physics that governs matter at those temperatures and luminosities. The objects caught in the act of crossing it are among the most dramatic in the galaxy. IRC plus 10,420 is 1. This star, observed intensively since the 1970s, appears to have been heating up at an observable rate. Its spectral type has changed measurably over the decades that astronomers have been monitoring it, suggesting it is moving through the void toward higher temperatures, in what is, by stellar standards, the blink of an eye. Watching a star change its fundamental character within a human observational lifetime is extraordinary. It speaks to how rapid the physics of the void can be. Rho Cassiopeiae provides an even more vivid demonstration. In 2000 and 2001, this yellow hypergiant underwent a violent outburst, expelling an estimated 3/100ths of a solar mass in a single event, its apparent temperature dropping by roughly 3,000 Kelvin in a matter of months. The star survived. But its violent response to crossing into cooler temperatures illustrated exactly the kind of instability de Jager's framework predicted. Now consider what this means for UY Scuti's future. If UY Scuti loses enough mass through its current red hypergiant winds and episodic ejections, its structure will eventually change. The outer envelope will contract, the star will heat, it will move to the left on the Hertzsprung-Russell diagram, crossing through progressively warmer temperature ranges. At some point, not imminent by any human timescale, but potentially within the next few 100,000 years, it will reach the temperature range of the yellow hypergiant void. What happens then is genuinely uncertain. It may be expelled back toward cooler temperatures, forced to shed more mass and try again. It may make it through, emerging on the hotter side as a different kind of object, smaller, hotter, bluer. Or it may not survive the crossing at all. The physics of the void does not guarantee passage. It guarantees disruption. Either way, the star that eventually crosses the void, if UY Scuti does, will not be the star we observe today. It will be a reduced, altered version, stripped of much of its outer envelope, carrying only the history of every mass loss event that came before. The record it currently holds, provisionally and uncertainly, will long since have ceased to be relevant. Most of what we understand about the interior lives of red hypergiants did not come from studying stars at 9,000 light-years. It came from studying the one that is close enough to examine in detail. Betelgeuse sits roughly 700 light-years from Earth, near enough that even before modern interferometers existed, astronomers could detect that it had a measurable angular diameter. Near enough that individual bright spots on its surface, structures comparable in scale to the distance between Earth and the Sun, have been resolved directly in images. Near enough that when something unexpected happens to it, the entire global network of observatories can pivot within hours and begin collecting data. It is a red supergiant rather than a red hypergiant, somewhat less massive, somewhat less luminous than UY Scuti, its radius estimated at somewhere between 700 and 900 solar radii depending on how the measurement is made and what phase of pulsation the star is in. It is not in exactly the same category as UY Scuti, but the underlying physics is the same family, the same pulsation mechanisms, the same mass loss processes, the same loosely bound outer envelope operating near the edge of gravitational stability. What Betelgeuse does, UY Scuti almost certainly does too, scaled up, further away, and far harder to observe. Guy Perrin at the Paris Observatory has been among those who have spent years building a precise picture of Betelgeuse through interferometric observation, accumulating measurements across multiple epochs and multiple wavelengths to characterize not just the star's size, but the structure of its extended atmosphere. That work has contributed to a picture of Betelgeuse as a dynamic, asymmetric, constantly evolving object, not the smooth, uniform sphere of a textbook diagram, but something turbulent and changing. Its surface marked by enormous convective upwellings, its extended atmosphere sculpted by the interaction between pulsation and mass loss. Then, in late 2019, Betelgeuse began to dim. This was not extraordinary at first. Betelgeuse is a variable star. It dims and brightens on multiple overlapping cycles. Observers had seen it faint before, but this dimming continued past the point of previous minima. By early 2020, it had dropped to the lowest apparent brightness ever recorded in the modern era, about 40% of its typical brightness, reducing it from one of the most prominent stars in the sky to something unremarkable to the casual eye. The speculation was immediate and intense. Had the dimming signaled the beginning of a supernova? Was Betelgeuse about to explode? It was not. When the full picture emerged over subsequent months, what had happened was something different, and in some ways more illuminating than a supernova would have been. Betelgeuse had undergone a surface mass ejection event. A region of the outer photosphere had been violently expelled, a mass of material estimated at several times the mass of the Moon, blasted away in a matter of weeks. As this material cooled and moved outward from the star, dust condensed within it. The dust cloud blocked some of the star's light from reaching Earth, producing the dimming. The star itself was unharmed. Once the dust dispersed and the disrupted photosphere recovered, Betelgeuse returned to something close to its normal behavior. What the Great Dimming revealed was a mass loss mechanism distinct from anything previously observed directly in real time for a star of this type. Not the steady wind, not the pulsational lifting of material at the photosphere. Something more abrupt, a localized violent expulsion driven by the same convective and pressure dynamics that operate throughout the envelope, but amplified in a single region to the point of rupture. The implications for understanding UY Scuti are direct. If Betelgeuse, a red supergiant substantially less extreme than UY Scuti, undergoes events of this kind, there is no reason to suppose that UY Scuti does not. The star almost certainly experiences comparable surface mass ejections, and their consequences are at least twofold. They contribute material to the circumstellar envelope that complicates measurement of the photospheric radius. And they represent an additional mass loss pathway, sitting alongside the steady wind and the pulsational contribution that has not been fully quantified for red hypergiants at UY Scuti's level of extremity. Here is the humbling part. Betelgeuse is on our doorstep, monitored continuously by some of the best instruments in the world. studied by generations of astronomers. And yet, the Great Dimming was not predicted. Not the timing, not the mechanism, not the scale of the ejection. It was recognized for what it was only in retrospect. If we cannot predict what Betelgeuse will do next week, what can we claim with confidence about UY Scuti, 13 times further away, far less monitored, at the edge of what current instrumentation can characterize? The answer is, rather less than the popular account of the largest known star would suggest. That does not mean the science is without value. It means that the confidence with which the headline circulates is somewhat ahead of the confidence the underlying measurements actually support. And that gap between headline and foundation is itself something worth understanding. Betelgeuse shows you what a red supergiant looks like in its precarious late phase. Eta Carinae shows you what happens when a star operates so far beyond its limits that the consequences are visible across the galaxy. Eta Carinae is roughly 7,500 light-years from Earth, in the southern constellation of Carina. By most measures, it is the most extreme luminous object in the Milky Way, radiating at several million times the luminosity of the Sun, pressing not just against, but through the theoretical boundary beyond which radiation pressure should prevent stability. It is not a red hypergiant. Its surface temperature is high, its color blue-white. It is a different kind of extreme, but its story is essential to understanding the boundary conditions that define what all extreme stars, including UY Scuti, can become. In the 1840s, Eta Carinae underwent what astronomers now call the Great Eruption. For roughly a decade, the system brightened dramatically until, at its peak around 1843, it became the second brightest star in the entire night sky, exceeded only by Sirius. This was visible from the southern hemisphere with the naked eye. Sailors used it for navigation, and then, over subsequent years, it faded, not because it exploded, but because the material it had ejected formed an expanding dust cloud that progressively obscured the star from optical view. The energy released during the Great Eruption was comparable to that of a supernova. The mass ejected has been estimated at somewhere between 10 and 40 solar masses, quantities of material that dwarf anything a red hypergiant sheds through its winds over comparable periods. And yet Eta Carinae survived. It is still there. Whatever mechanism drove the eruption did not destroy the star. It stripped away enormous quantities of its envelope, reshaped its immediate environment, and left behind the extraordinary bipolar nebula of gas and dust that surrounds it today. The Homunculus Nebula, visible through modest amateur telescopes as two lobes of glowing material expanding outward from the star at roughly 650 kilometers per second. Richard Stothers, at the NASA Goddard Institute for Space Studies, worked on the theoretical mechanisms behind such events. The dynamical instabilities that can drive a star to expel near supernova quantities of mass while leaving the core intact. His work identified the conditions under which the envelopes of extreme luminous stars become so dynamically unstable that a super-Eddington eruption develops, an outflow of material at a rate that briefly exceeds what radiation pressure alone should be able to sustain. The physics involves the coupling between the pulsational instability of the envelope and the opacity behavior of stellar material near the temperatures and pressures found in these outer layers. Under the right conditions, a runaway develops. The result is an eruption that is not a supernova, but looks, from a distance, almost like one. Eta Carinae is now understood to be a binary system. The primary star, a luminous blue variable estimated at around 90 solar masses in its current depleted state, orbited by a massive companion on a highly eccentric orbit with a period of 5.5 years. Every time the companion swings to its closest approach, the interaction between the two stellar winds creates intense X-ray emission detectable across interstellar distances. The companion's presence may have influenced the asymmetry of the Great Eruption and the bipolar geometry of the homunculus, though the details of this interaction remain a subject of active investigation. What Eta Carinae tells you about UY Scuti's fate is something specific and important. The endpoint of a massive star's life is not determined simply by how massive it was at birth. It is determined by how much mass it retains through its entire evolutionary history. And that history is shaped by every wind, every eruption, every binary interaction, every crossing of the instability region that the star experiences between birth and death. A star that begins life at 30 solar masses and loses 10 of them quietly through winds will die differently from a star that begins at the same mass and loses 10 solar masses in a single catastrophic eruption during a luminous blue variable phase. The total mass shed may be identical. The timing, the rate, the chemical composition of the ejected material, and the state of the core at the moment of death will all be different. And those differences determine whether a neutron star forms, or a black hole, or whether the core collapses so completely that nothing survives at all. Uy-Scuti's final state cannot be read off from a single number. It is buried in a history of mass loss that we can partially reconstruct from the circumstellar envelope around it, partially infer from what we know about stars in similar evolutionary phases, and partially, perhaps substantially, cannot know at all. Eta Carinae exists as a reminder that even the most luminous, most studied, most extreme objects in the Milky Way can surprise us with the violence and scale of what they do. Uy-Scuti, quieter for now, carries the same potential for unexpected behavior, compressed into a timeline we cannot fully see. At some point, not in any time frame that means anything to a human life, but real and inevitable by the standards of stellar physics, Uy-Scuti's core will run out of fuel. The sequence is already underway. In the core of the star, fusion has long since moved past hydrogen. Hydrogen burning is a main sequence process, and Uy-Scuti left the main sequence millions of years ago. What is happening in its core now is the later chapters of the nuclear story. Helium fusing into carbon and oxygen, carbon burning into neon and magnesium, each successive stage shorter than the last, each producing progressively less energy per unit of fuel consumed, each leaving behind a core that is denser, hotter, and closer to the end of what nuclear physics can offer. The timescales compress dramatically as the burning advances. Hydrogen fusion in a massive star runs for millions of years. Helium fusion for hundreds of thousands. Carbon burning for perhaps 1,000 years. Neon burning for a year. Oxygen burning for months. Silicon burning for days. Each stage extracts what energy it can from a progressively heavier set of elements, building an onion-like structure in the core, shells of different burning stages nested around a central region of ever-increasing density and temperature. At the center of that onion, silicon fusion is building iron. Iron is the endpoint. It is the most tightly bound nucleus in nature, the element for which fusion yields no net energy and for which fission would require energy to be added rather than released. When the silicon burning shell has produced an iron core of approximately 1.4 solar masses, the game is over. There is no fuel left that physics will let the star burn. The core has nothing left to give. What happens next takes place in less than a second. With no outward pressure from fusion to balance the inward crush of gravity, the iron core collapses. Not gradually, instantaneously, in stellar terms. The collapse proceeds at roughly a quarter of the speed of light. A core that moments before occupied a volume comparable to the Earth is compressed, in roughly 200 milliseconds, into an object roughly 20 kilometers across. The density reached is nuclear density, the density of an atomic nucleus, applied to an object containing more mass than the Sun. A teaspoon of the resulting material, if you could somehow transport it to Earth, would weigh in the region of 10 billion tons. The energy released in those 200 milliseconds is staggering. The gravitational potential energy liberated by the collapse is roughly 3 times 10 to the power of 46 joules, more energy than the Sun will emit across its entire 10 billion year lifetime. The overwhelming majority of it escapes not as light, but as neutrinos, ghostly particles that interact so weakly with ordinary matter that they pass through the entire remaining star in seconds, carrying with them an energy budget that dwarfs everything happening in the visible universe at that moment. A tiny fraction of that energy, roughly 1%, is deposited in the infalling outer material of the star. And that fraction is enough. The outer layers, falling inward toward the collapsed core, slam into the newly formed neutron star and rebound. The resulting shockwave propagates outward through the star's envelope at speeds of tens of thousands of kilometers per second. If the shock is strong enough, if it is not stalled by the enormous pressure of infalling material and revived by the neutrino flux, it reaches the photosphere, and the outer layers of the star are ejected into space at velocities that would carry them across the solar system in hours. This is a core collapse supernova. In the days and weeks that follow, the expanding ejecta glows, initially from the shock itself, then from the radioactive decay of nickel-56 produced in the explosion, then from the light echoing off surrounding circumstellar material. At peak brightness, a supernova of this type can outshine an entire galaxy of hundreds of billions of stars for a brief interval. The light is visible across cosmological distances. But here is where U.Y. Scooty's story becomes genuinely uncertain, and where a piece of work that originated at Queen's University Belfast in Northern Ireland becomes directly relevant. Stephen Smart had been studying the progenitors of core collapse supernovae, searching through archival images taken before supernova events occurred, looking for the stars that had exploded, characterizing their properties. The goal was to build a population-level picture of which kinds of stars produced which kinds of supernovae. For several supernova types, the program worked well. Progenitor stars were identified, their masses estimated, a coherent picture assembled. For the most massive red supergiants, stars with initial masses estimated above roughly 18 solar masses, the program found something troubling. The progenitors were absent, not poorly constrained, not difficult to identify, but statistically absent from the survey in numbers that could not be explained by observational limitations alone. When Smart and colleagues assembled the statistics, the message was clear. The most massive red supergiants in the sky are not the stars that explode as the supernova we observe. They are going somewhere else. This became known as the red supergiant problem. It has generated considerable discussion and competing explanations since its identification, but the most direct interpretation is that very massive red supergiants, including, potentially, stars like U.Y. Scuti, do not produce conventional visible supernova at all. Instead, their cores collapse directly to black holes, and the envelope either falls in silently or is expelled weakly without producing the weeks-long brightening of a standard core collapse event. Alexander Heger and Stan Woosley at the University of California, Santa Cruz had mapped out, from theoretical first principles, how a star's initial mass relates to its final fate, the remnant type it leaves behind. Their mass-fate diagram showed that the relationship between birth mass and death outcome is not a simple monotonic function. It is complicated and in places counterintuitive, with stars of certain mass ranges producing neutron stars, others producing black holes, and some, in specific windows shaped by the details of how mass loss and nuclear burning interact, potentially collapsing to black holes with no visible supernova at all. Where U.Y. Scuti falls on that diagram is not known. Its current mass is estimated somewhere between 7 and 32 solar masses, a range wide enough to span multiple distinct outcome categories on the Heger-Woosley map. Its initial mass is inferred to have been somewhere in the range of 25 to 40 solar masses, but that inference depends on assumptions about its mass loss history that carry their own uncertainty. The honest answer to the question of what U.Y. Scuti will leave behind is that we do not know. It might produce a conventional core collapse supernova, briefly visible to observers in nearby galaxies. It might collapse silently, the star simply disappearing from the sky over the course of a few days. It might leave a neutron star. It might leave a black hole. The uncertainty is not a gap to be embarrassed about. It is a direct consequence of the genuine complexity of the physics involved, and the genuine limits of what current observations of this particular star can tell us. If U.Y. Scuti does produce a visible supernova, if the shock wave makes it out, the object left at the center of the explosion will depend critically on what happens in the final fractions of a second of the core's collapse. For the majority of core collapse supernovae, the remnant is a neutron star, an object 20 kilometers across, containing between 1 and 2 solar masses of material compressed to nuclear density, spinning rapidly, threaded by a magnetic field that makes anything in ordinary experience look negligible. Freshly formed neutron stars can rotate hundreds of times per second. The angular momentum of the collapsing core, conserved as the radius shrinks by a factor of tens of thousands, concentrates into a spin rate that would fling apart any ordinary material. Over time, the rotation slows as the magnetic field carries away energy. Most neutron stars we observe are old enough that they pulse at rates of seconds. The well-known pulsars, flashing radio beams like lighthouses as they spin. The magnetic field strength has decayed from whatever it was at birth. The neutron star has settled into a long, quiet existence that will last longer than the current age of the universe. But some neutron stars are born differently. If the progenitor core is rotating rapidly enough, and if conditions during the collapse are right, the resulting neutron star may emerge with a magnetic field not in the range of a typical pulsar, but orders of magnitude more intense, a field approaching 10 to the power of 15 Gauss, 1 trillion times stronger than the Earth's field, and roughly 1,000 times stronger than an ordinary pulsar. This is a magnetar. Magnetars do not behave like ordinary neutron stars. The energy stored in a magnetic field of this strength is enormous, comparable in some estimates to the energy released in a supernova, and it cannot remain stored indefinitely. It is released gradually and sometimes suddenly through a process involving the crust of the neutron star. The rigid crust, threaded by field lines under enormous tension, cracks. Starquakes propagate through the interior. The sudden reorganization of the magnetic field releases energy in intense bursts of X radiation and gamma radiation that can, in the most extreme cases, be detected across tens of thousands of light years. In 2020, a magnetar in our own galaxy produced something that changed how scientists think about one of the deepest mysteries in observational astronomy. The source, designated SGR 1935 plus 2154, released a burst that was simultaneously detected as a fast radio burst, a millisecond duration pulse of radio emission of a kind that had previously been observed only from cosmological distances, with no identified source and no agreed mechanism. The detection established definitively that at least some fast radio bursts are produced by magnetars, and it did so by catching the equivalent event occurring within our own galaxy for the first time. Think about that chain of connections. A hypergiant star, somewhere in the galaxy's history, collapses. From its core, a magnetar forms. That magnetar, millions of years later, releases a starquake, and from that starquake comes a burst of radio waves lasting a millisecond, the same kind of signal that astronomers had been detecting from the distant universe for years without understanding what produced it. UY Scuti might, if the right conditions hold during its eventual core collapse, produce a magnetar. The mass we estimate it retaining, the rotation we infer from its current state, the binary history we cannot fully reconstruct, all of these feed into whether the remnant would be an ordinary neutron star, a magnetar, or something else entirely. The irony is almost too neat to state plainly. A star that has spent several million years as one of the physically largest objects in the Milky Way, a star whose radius today spans what would be the inner solar system, might end its existence as an object 20 kilometers across, not larger than a city, and yet in the magnetic field strengths and energy densities it generates, in the violent phenomena it produces, this 20-kilometer object would be more extreme than anything the living star ever managed across its entire enormous surface. Size and extremity, it turns out, are not the same thing. They never were. There is another possibility, one that sits at the darker end of the outcome spectrum, and one that has moved, in recent years, from theoretical curiosity to something with genuine observational support. A massive star's core collapses. The shockwave forms. But the shock is not strong enough. It stalls, halted by the crushing pressure of material still falling inward, unable to push outward against the weight of the entire remaining stellar envelope above it. the neutrinos streaming out from the proto-neutron star deposit energy into the stalled shock, but not enough. The shock retreats. The envelope that was beginning to be expelled falls back. The neutron star continues to accumulate mass beyond the point at which neutron degeneracy pressure can hold it. And then it too collapses into a black hole. The star does not explode. It implodes. The entire object, a hypergiant that might have filled the inner solar system, that had been shedding mass for millions of years, that was one of the largest things in the galaxy, simply disappears from the visible sky. What remains is a black hole and the slowly dispersing remnant of the circumstellar envelope that had been expelled in the millennia before death. No weeks-long brightening, no expanding shell of heavy elements seeded into the interstellar medium. Just absence. This is the failed supernova, and there is now at least one candidate for it having actually happened. Christopher Kochenek at Ohio State University led a long-term survey program monitoring a sample of nearby galaxies, watching individual stars across years of observation, looking not for things that appeared, but for things that vanished. The logic was straightforward. If failed supernovae occur, the stars that undergo them should simply disappear from one epoch of observation to the next. No explosion, no afterglow, just a gap where a star used to be. In the galaxy NGC 6946, a face-on spiral roughly 22 million light-years away, sometimes called the Fireworks Galaxy, for the unusually high rate of conventional supernovae observed within it, a red supergiant designated N6946-BH1 behaved strangely in 2009. It brightened briefly, producing a faint optical transient that might have been a precursor outburst or the initial shock breakout from an implosion. Then it faded. Then it was gone. Follow-up observations with the Hubble Space Telescope confirmed that the star had disappeared from its pre-outburst position. Nothing remained at the location bright enough to be the original star. A faint infrared source, possibly the warm dust of the ejected circumstellar material, persisted, but the star itself had vanished. N6946-BH1 is not a confirmed failed supernova. Alternative explanations exist. The star could have been obscured by newly formed dust, or have merged with a companion in a manner that reduced its optical luminosity without destroying it. But the case remains among the most compelling evidence that the phenomenon is real and that it occurs in stars in the mass range relevant to this discussion. Think about what this means for UY Scuti's place in the sky. If a failed supernova is the outcome, if UY Scuti's core collapses and the shock cannot escape, then some point in the future, from the perspective of any observer elsewhere in the galaxy, the star will simply not be there anymore. No warning, no months of brightening. The light from the final moments of the photosphere will arrive at Earth perhaps 9,500 years after the event, and to any telescope pointed in that direction, there will be a gap in the star field where UY Scuti used to be. The broader implications extend beyond any individual star. Models of how galaxies evolve depend heavily on stellar feedback, the energy that massive stars inject into the surrounding interstellar medium through their winds, their radiation, and above all their supernovae. That energy heats the gas, drives turbulence, suppresses or triggers new star formation, and shapes the structure of galaxies across cosmic time. Supernovae are the dominant energy source in this picture. A conventional core collapse supernova deposits roughly 10 to the power of 44 joules into the surrounding medium, the 1% of the neutrino energy that couples to the ejector. A failed supernova deposits a small fraction of this. The neutrinos still escape. The gravitational potential energy is still released. But without the shock-driven ejection of the envelope, the surrounding interstellar medium receives far less energy. If a significant fraction of the most massive stars, precisely the stars that would otherwise be the most energetic supernovae, end their lives silently, the total energy budget of stellar feedback in galaxies is lower than models assuming complete supernova production would predict. The red supergiant problem and the failed supernova hypothesis are, in this sense, two faces of the same realization. The most massive red supergiants are not producing the supernova we would expect them to produce. Either they are collapsing directly without a visible explosion, or they are evolving into a different stellar type before dying, or something else is happening that current models do not fully capture. Understanding which of these alternatives is correct, and in what proportions, is one of the open questions at the frontier of stellar astrophysics. UY Scuti sits squarely in the parameter space where this uncertainty is most acute. All of this raises a question that underlies every calculation discussed in this video and every size ranking ever assembled for the most extreme stars known. Is there a limit? Not just an observed upper boundary like the Humphreys-Davidson limit, an empirical ceiling derived from looking at the sky and noticing what is absent, but a hard physical ceiling, a point beyond which the laws of nature simply prohibit a star from growing. The theoretical answer begins with Arthur Eddington's luminosity limit, already encountered in the context of the Humphreys-Davidson discussion. At a certain luminosity, for a star of a given mass, radiation pressure balances gravity. Above that luminosity, the star cannot hold its outer layers. The Eddington limit predicts a maximum luminosity for a given mass, and equivalently, a maximum mass for a star that maintains a given luminosity. For stars radiating near their Eddington luminosity, as the most massive stars do, mass loss rates become enormous, and the stars shed material so rapidly that their mass, and therefore their maximum sustainable luminosity, continuously decreases. In practice, this means that there is a kind of dynamic ceiling. A star cannot form and remain stable above a certain mass because it would immediately begin losing mass at a rate that brings it back below the threshold. The question is where that threshold sits. Paul Crowther at the University of Sheffield led the analysis that pushed the accepted answer upward significantly. Working with collaborators on observations of the R136 cluster at the heart of the Tarantula Nebula in the Large Magellanic Cloud, his team used spectroscopic and photometric data from the Hubble Space Telescope to disentangle the light from individual stars within a region so dense and so luminous that isolating single objects requires exceptional resolution. What emerged from that analysis was a set of stars with masses estimated at between 150 and 300 solar masses, well above the previously accepted upper limit of 150 solar masses that had stood in the literature for decades. R136A1, the most massive of these objects, has a radius of perhaps 35 to 40 solar radii, enormous by ordinary stellar standards, but a rounding error beside UY Scuti. It is blue-white, ferociously hot, radiating at perhaps 8 million times the luminosity of the Sun. It is the most luminous star known, and it is losing mass at a rate that will reduce it substantially over its remaining lifetime, a lifetime measured in a few million years at most before its core collapses. The distinction between R136A1 and UY Scuti is the distinction between mass and radius, and it is fundamental. A star's physical size depends not only on how much material it contains, but on what temperature that material is radiating at. The Stefan Boltzmann law is precise on this point. For a given luminosity, a cooler surface requires a vastly greater surface area to radiate that energy away. UY Scuti is cool, roughly 3,200 Kelvin. Its luminosity, while enormous by solar standards, is modest compared to R136A1. But to radiate even that modest luminosity at such low temperatures, the surface area must be colossal. The radius is the consequence of the temperature, not simply the mass. This is why the largest star and the most massive star are different objects. It is why they will probably always be different objects. The physical limit on radius is set not by mass alone, but by the combination of luminosity and temperature. And the combination that produces the greatest physical radius is a cool star radiating at a luminosity just sufficient to keep the envelope inflated against gravity. Red hypergiants sit in exactly this regime. Whether UY Scuti is near the practical limit of how large a cool stellar photosphere can become in the current universe is not known. Theoretical models of stellar structure suggest that there are limits beyond which radiation pressure prevents further envelope inflation, that for a star of a given luminosity, the envelope cannot expand without bound, because as it expands it cools, and as it cools the opacity and radiation pressure dynamics change in ways that eventually stabilize the radius. Whether UY Scuti's measured radius, contested, uncertain, somewhere in the vicinity of 1,500 to 1,900 solar radii, sits near that stabilization point is an open question. In the very early universe, before the first heavy elements had been forged and distributed by the first stellar generations, conditions may have permitted objects far larger. Theoretical models of so-called quasi-stars, hypothetical objects in which a black hole forms at the center of a still accreting gas cloud, with the surrounding envelope stabilized by the energy released from accretion, suggest sizes of tens of astronomical units. 1 astronomical unit is the distance from the Earth to the Sun. Tens of astronomical units would be a radius reaching to the orbit of Saturn or Neptune. Beside a quasi-star, UY Scuti would be a modest object. Those hypothetical behemoths, if they existed at all, are long gone. The universe has cooled. The conditions that might have permitted them no longer obtain. What we have now, at the upper extreme of what stellar physics permits in the present cosmos, are objects like UY Scuti, red hypergiants pressing against the Humphreys-Davidson limit, losing mass rapidly, unstable, brief, and apparently sitting near the ceiling of physical size that the current universe allows. Whether they are at that ceiling, or merely approaching it, is another question that nobody has yet answered cleanly. There is a version of this story that presents the uncertainty around UY Scuti's size as a failure, as science not yet having done its job properly, as a gap waiting to be closed. That framing is understandable. It is also, on reflection, wrong. Consider what the measurement problem actually consists of. You have a star 9,500 light-years from Earth. It sits in one of the most heavily obscured regions of the inner Milky Way, embedded in a dense field of foreground and background stars that complicate every observation made of it. It is surrounded by a circumstellar envelope of its own making, expelled material that blurs the boundary between the star and the space around it at every wavelength. Its photosphere is not a clean surface, but a dynamic, extended atmosphere whose altitude varies by hundreds of solar radii across a pulsation cycle of nearly 2 years. The angular diameter it presents to our instruments is roughly 5 milliarc seconds, an angle small enough to fit hundreds of thousands of times within the disk of the Moon as seen from Earth. To measure the physical radius of this object, you must first measure that angle precisely, using an interferometer whose baselines extend to hundreds of meters, and whose optical alignment must be maintained to tolerances of fractions of a wavelength of light. Then, you must convert that angle to a physical length, which requires knowing the distance to a precision that the best space-based astrometry mission ever built is still struggling to achieve at this range. Then you must account for the fact that the angle you measured corresponds to a photosphere whose definition depends on the wavelength you used and the atmospheric model you adopted. Then you must acknowledge that whatever number you produced is the radius on the specific night or nights your observation was made. Not the mean radius, not the maximum, not a time-averaged value, but a snapshot of a moving target. The fact that Begoña Arroyo Torres and her collaborators produced a number at all, a real, physically grounded, interferometrically derived measurement, is not a modest achievement. It is remarkable. The fact that Gaia then provided a revised distance that propagated through the calculation and shifted the answer is not a setback. It is how science is supposed to work. Each iteration of the measurement is more constrained than the last. Each new instrument or data release tightens a different link in the chain. Astronomy is, more than almost any other science, a discipline of inference rather than direct measurement. You cannot visit a star. You cannot sample its atmosphere or run a controlled experiment. Everything you know about UY Scuti was derived from photons, from light collected by telescopes on a mountain in Chile and a satellite 1.5 million kilometers from Earth, interpreted through mathematical models, filtered through a century of accumulated stellar physics. Each link in that chain introduces uncertainty. The uncertainty compounds. And at the end of it, you have a number with error bars large enough to include multiple competing candidates for the same title. This is not a scandal. It is a precise description of where the science stands. The title of this video is not provocative framing. It is an accurate summary of the situation in the peer-reviewed literature. Nobody agrees on how big this star actually is, not because the scientists involved are careless or incompetent, but because they are working at the absolute frontier of what current instruments can resolve, on an object that is doing everything in its power to resist characterization. That frontier is exactly where science is most alive. The frontier, though, is not static. The instruments that will substantially narrow the uncertainty around UY-Scuti's size are either already operating in improved configurations or under active construction. The question is not whether the answer will improve. It is when and by how much. The most immediate near-term improvement to the angular diameter measurement comes from developments on the Very Large Telescope Interferometer itself. The Gravity Plus program, an upgrade to the gravity instrument that operates in the near-infrared on the 4-telescope array at Paranal, is designed to extend the sensitivity and precision of interferometric measurements to fainter targets than were previously accessible. Red hypergiants at UY-Scuti's distance are marginal targets for the current generation of interferometric instruments. Gravity Plus is intended to push that margin outward. A new angular diameter measurement of UY-Scuti made with improved sensitivity at multiple epochs spanning a full pulsation cycle would address both the angular precision problem and the pulsational phase problem simultaneously, producing not a single snapshot radius but a characterized range. The distance problem, the other great source of uncertainty, requires a different approach. Gaia has done what it can at this distance, and its precision, while transformative for the broader stellar census, leaves UY-Scuti's parallax uncertain enough to matter. The obvious solution is an astrometry mission with greater precision than Gaia, and proposals for exactly this have been developed within the European Space Agency and elsewhere. A successor mission capable of micro-arc-second or sub-micro-arc-second parallax precision for stars at UY-Scuti's distance would reduce the fractional distance uncertainty to a level where the propagated radius uncertainty is dominated by the angular diameter measurement rather than the distance. At that point, a clean interferometric angular diameter measurement and a clean distance would together produce a radius estimate precise enough to resolve the contest between UY-Scuti and its rivals. The extremely large telescope, under construction at Cerro Armazones in Chile, 39 kilometers from the Very Large Telescope site at Paranal, brings a different capability. With a primary mirror 39 meters across, more than 3 times the diameter of any existing optical telescope, it will collect light at a rate that dwarfs current facilities. For a star like UY-Scuti, this means spectroscopic observations of unprecedented quality, detailed characterization of the stellar atmosphere, the effective temperature, the chemical composition, and the circumstellar environment, all of which feed into the modeling that converts angular diameter to physical radius. The uncertainty in the atmospheric model used to interpret the interferometric measurement is currently a non-trivial contributor to the overall radius uncertainty. Extremely large telescope spectroscopy could substantially reduce it. The square-kilometre array, under construction across sites in South Africa and Australia, approaches the problem from a different direction entirely. Radio interferometry at centimetre wavelengths can resolve the radio photospheres and circumstellar envelopes of nearby radio-bright stellar sources at resolutions comparable to the best optical interferometers, and because radio emission from these stars does not suffer dust extinction the way optical emission does, it provides information about the stellar environment that optical observations cannot access. For stars embedded in heavy dust, as UY-Scuti is, Radio imaging offers a complementary and in some ways cleaner view. What none of these instruments will fully resolve is the intrinsic variability of the star. UY Scuti will still be pulsating when the extremely large telescope first light arrives. It will still be shedding mass, still be changing radius across a roughly 740-day cycle, still be a moving target. The best that improved instruments can do is characterize that variability precisely, to determine the mean radius and the amplitude of the variation with enough confidence that the measurement finally means something definitive. That characterization is coming. The timeline is uncertain, but the direction is clear. The question of how big UY Scuti actually is will be answered, more precisely than it has been, possibly precisely enough to settle the record. The answer will not look like a single number. It will look like a range, defined by the pulsation, with a central value and uncertainties small enough to compare meaningfully against those of every rival candidate. The record will be settled. It just has not been settled yet. Come back to the beginning. Come back to where this started. Not with a measurement, not with an instrument, not with a number, but with the thing itself. Somewhere in the direction of the constellation of Scutum, 9,500 light-years from where you are, there is a star whose outer atmosphere extends across a volume that would consume the inner solar system. The photosphere, wherever the precise boundary sits, glows deep orange at roughly 3,200 Kelvin, steadily shedding material into the space around it, swelling and contracting across a cycle nearly 2 years long. The star is surrounded by the record of its own past, an expanding shell of gas and dust that traces the history of every mass loss event going back millions of years. The light from that star that is reaching Earth right now left the photosphere before the first cities were built, before writing existed, before agriculture. The measurement that produced the number 1708 solar radii is a portrait of the star as it was when human civilization was finding its feet. The dispute about whether that number is correct and whether it places UY Scuti above or below its rivals is a dispute about the state of an object 9,500 years in the past. If UY Scuti has already died, if its core has already collapsed in the interval between then and now, we will not know for 9.5 millennia. It might have exploded already. It might have vanished. The star we argue about may no longer exist. We are measuring history. What the existence of UY Scuti reveals about the universe is something worth sitting with. The laws of physics, the same laws that govern the behavior of matter at every scale, from the nucleus of an atom to the largest structures in the cosmos, permit, under specific conditions, the formation of objects of this size. There is nothing in the fundamental constants of nature that requires stars to exist at all, let alone stars 1,500 to 2,000 times the radius of our own. The existence of red hypergiants is a statement about what the combination of gravity, nuclear physics, and radiation pressure allows when you push them to their limits. Those limits matter for the matter you are made of. The iron in your blood was forged in the core of a massive star and scattered into the interstellar medium by its explosion. The oxygen you breathe has the same origin. The calcium in bone, the phosphorus in DNA, each element beyond iron on the periodic table, forged in the final seconds of a core collapse or in the neutron-rich environment of a neutron star merger, seeded into the galaxy by the deaths of objects like UY Scuti over billions of years. Every atom above a certain atomic number in your body passed through the interior of a dying massive star before it became part of a molecular cloud, before it became part of the solar system, before it became part of you. UY Scuti is not a spectacle. It is a participant in the chemistry of the cosmos. When it dies, in whatever manner physics eventually demands, the material it has been slowly releasing for millions of years and the heavier elements forged in its core over its entire evolutionary history will join the interstellar medium and eventually find their way into something new. The reason nobody can agree on how big this star actually is turns out to be inseparable from everything else about it. It is hard to measure because it sits at the boundary of what stars are permitted to be. It is at that boundary because the forces operating within it are in near balance, gravity and radiation pressed against each other across a volume so enormous that small perturbations propagate through the whole structure as slow, years-long oscillations. The pulsation that makes it a moving target is the same physics that makes it extreme. The mass loss that obscures its photosphere is the same physics that will eventually determine what it leaves behind. Every complication in the measurement is a direct consequence of the physics that makes the measurement worth attempting. We have spent this time examining the edges of what we know about one star, its size, its distance, its variability, its place in the galaxy, its past, and its future. What we have found at those edges is not emptiness. It is more questions, good questions, the kind that point toward instruments being built, observations being planned, and measurements not yet made. The life and death of UY Scuti will unfold across timescales no single human civilization will witness from beginning to end. We have caught it in a single frame. The frame is blurred at the edges, uncertain in its details, contested in its headline number, and it is one of the most extraordinary things anyone has ever tried to look at.